So I am going to define an operator, a linear operator called L pi. Okay. So L pi is something that is going to take a vector from the space V, where capital V is the space of all value functions, right. So capital V is a complete normed vector space of all value functions, right. So I am going to define an operator L pi that takes an element in V to another element in V, right. So how will I define L pi? L pi operating on V will give me back a function that is right. So V is some element in capital V, so it is some value function, okay, or rather some element in capital V, okay. So what is the difference between saying that it is some value function and then saying some element in capital V? When I say it is a value function, I am kind of implicitly saying that there is a policy for which that is the expected return, right. But when I say it is a point in the space V, that need not necessarily be true. I mean it is just some point in a S dimensional space, that need not necessarily exist a policy corresponding to that function, okay. So I am just saying it is some function V, right, that exists in that space capital V.
What is the right hand side space? V to V?
V to V.
The other space?
What other space?
Or same space?
V to V. Yeah. Right. Does that make sense? I mean, is that confusing to people? Yes, everybody is on board, right? Good. Right. So what does my Bellman equation tell me? If you think about it, the Bellman equation tells me right, that is what my Bellman equation is telling me. Essentially it is saying that I take this point V pi in the space capital V, I apply the operator L pi on it, whatever it gives me back will be V pi, right. So likewise if I can define an operator for the optimality equation, it will tell me that V star is a point in space V such that if I apply the operator, let us call it L, if I apply L on it, it will give me back V star. So this implies that V pi is what is known as a fixed point of L pi, right. So if you think about it, right, so normally I take some vector V, I apply L pi on it, okay, it will go to some other point, then I will apply L pi on it, it will go to some other point, then I will apply L pi on it, it will keep moving around, right, in space, right. If I apply L pi on it and it stays there, then I call it a fixed point.
What is the
because I am defining the operator through R pi and P pi, which themselves are defined through pi, right. I mean if you remember the definition of R pi.
Independent of pi.
No, it is not. No, because the mapping is R pi, I mean the mapping uses R pi and P pi as integral components of it, right. So it is not independent. So the other one is independent, there we will drop the dependence. The optimality equation has no dependence on pi, there we will drop the dependence on pi, but the Bellman equation has the pi in it. Okay. Great. So I will introduce you to something called the Banach fixed point theorem, okay, which is a very basic, I mean believe it or not, whatever we are doing is very fundamental stuff, right, very minimal math in terms of trying to prove convergence and things like that, because I have restricted you to finite MDPs, okay. So the more hairy, the more interesting math comes when you start operating in the infinite state spaces, right, where I mean you can't write down simple results, okay, you have to have lot of qualifications. if your MDP says that S satisfies this and that and A satisfies this and that, then something will hold, right. But here we can say we can write very easy results. So I am going to use something called the Banach fixed point theorem, okay, which makes our life a lot easy, right. Sounds like a very fancy term, right? Banach space. So what is a Banach space? We already know what a Banach space is. Complete normed vector space is called a Banach space. Okay, just don't get put off by terminology. We understand this, right? So we know what a Banach space is. A complete normed vector space is a Banach space, right? So one thing which I forgot, I will introduce it later just now, okay. So some mapping T that maps points in U to another point in U, right. We assume it is a contraction mapping. I will tell you what is a contraction mapping in a minute, okay. But you can kind of guess what a contraction mapping is, right. It takes 2 points in space, right. I take U and V, okay, I take T of U and I take T of V, right. So T of U and T of V will be closer to each other than U and V were, right. So that is essentially a contraction mapping. So I will write it down formally in a minute, right. Then okay, so what we are saying, suppose U is a Banach space and T is a contraction mapping, essentially things that brings points together, then there exists a unique V star in U such that T V star equal to V star. So that essentially means that T has a fixed point, T has a fixed point and it is a unique fixed point, okay. And the second thing is, for arbitrary starting point V naught, if I keep repeatedly applying T on V naught, right, I will converge to V star, right. So showing 1 does not imply 2, okay, just because a fixed point exists, right, repeatedly applying it did not necessarily converge to the fixed point. In fact, there are some results for certain algorithms where we can show that algorithm itself has a fixed point, right, I mean, or rather the system of equations you set up itself has a fixed point, but the iterative process that you are using for solving it did not necessarily converge to it, okay. There are cases that will happen, but in this case it turns out that repeatedly applying T, that is essentially what the sequence is, right. I start off with V naught, I apply T on it once, I get V1, I apply T on it again, I get V2, I apply T on it again, I get V3 and so on and so forth, right. I keep doing this, well, often enough, right, I will end up in V star. Right. So how many times is often enough is something we will study when we look at actual algorithms for solving these problems, but these are the things, right, that exists a unique V star, and this are the a couple of things that we need to show. One is that U is a Banach space. Yeah.
Why are you calling it fixed point? Isn't it like a whole line?
Oh.
It's basically an eigenvector of alpha, right?
Well, it's a point, right? It's a point in the V space, right? It's eigenvector, fine, but eigenvector is a point in the V space. No,
It's a line in the V.
it's a point in the V space, right? That's what we have been saying. So what is V pi? V pi is a vector that the first component is V pi of 1, then V pi of 2, V pi of 3, V pi of 4. So it's simply a point in a S dimensional vector space. Right? Confusing? Okay, let's think of a case where there are two states alone. Let's state 1, state 2. Right? I define some policy. I'm just going to cook up something. Let's look at how it works. I have 1, I have 2. Okay. Some arbitrary thing, I have written an MDP for you here, right? So I take action 1 from state 1, I will go to state 2, I will get a reward of 1. I will take action 1 in state 2, I will go to state 1 with a reward of 1. I take action 2 in either state 1 or state 2, I am going to stay there with a reward of -1. Okay. Now let me define a policy. So what is a policy? Pi of 1 is A1 and pi of 2 is A2. I determine, A1, pi of 2 is A1, let us just define A1 for both, right. So what is the value of state 1 under pi? I mean, you can do it easily enough, but for some value of gamma you can solve it, or you can just write the summation, right? It's just 1 plus gamma squared plus gamma cubed. I mean, you can solve this system of equation, or you can just tell me what is the limit of the summation. Somebody tell me. Yeah. Right. Now if I think of this in a two-dimensional space, so I have a two-dimensional space, this dimension is V pi of 1, this dimension is V pi of 2, just a point. So this point is, this I shouldn't say pi, V of 1. Now we can think of defining a pi prime, which is like same minus of that, right? Right. So for any policy I choose like this, right, pi of A1 and pi of A2, whatever things I choose, I am going to end up with some point in this space. Right. So this is what I mean by the space capital V. So this is my space capital V, and each value function is a point in this space. Right. I mean, I was hoping people had actually this this in their mind when they were nodding with whatever I was saying earlier. Right. So this is what I mean by saying all of these things which we have talked about, right, this being a complete normed vector space, everything we have talked about is with this picture in mind. Right. So Okay, does it make sense? Any questions about that? Of course, I just chose deterministic policies to be easy, right? You could choose stochastic policies, you just have to write out this more terms in this equation, right? This equation will have the sum over pi SA, right, and then you solve it and then you get it, right. So essentially the tricky part here turns out showing that whatever mapping T you are considering is a contraction mapping. So if you can show whatever is the map that you consider, in this case we are going to be considering L pi, if you can show that L pi is a contraction mapping, right, then you get the rest of it for free. Yeah, so that's it, essentially that's what you have to do to show it's a convergent, it's a contraction mapping. I'll just tell you in a minute. I'll formally write down what a contraction mapping is. Okay. Right. So for sure, okay, it moves away. Right. So this is what a contraction mapping is. So if U and V were some distance apart, after I apply T on both of them, they will be closer than what they were earlier, right, by a factor of at least lambda, right, where lambda lies between 0 and 1, right, 1 excluded. Okay. So the smaller the value of lambda, what does it mean? The faster the points are brought together, the more the contraction is, right. The closer the value of lambda is to 1, the lesser the contraction is. Obviously lambda equal to 1 does not make sense, right. If lambda is 1, then there is no contraction. Okay. If lambda 1 is T identity, need not be. I am just telling you, just the distance have to be preserved, right. I can swap U and V also, right. Just remember that. Okay, so now let us look at the proof of the Banach fixed point. So why is it called the Banach fixed point theorem?
There is a fixed point to which all the other.
Because it applies in Banach space, right. So for different kinds of spaces that you are starting off with, you have different kinds of fixed point theorems. There is a whole family of fixed point theorems, okay, depending on the underlying assumptions you make. So this is a fixed point theorem that will show in the Banach space. It is one of the simplest of the fixed point theorems. Okay, so if you have lesser restrictions on the underlying space, then the showing fixed points becomes more tricky. Okay. So here is the trick that we will be using repeatedly. Okay, I am just taking some iterates in that sequence, right. So I have taken some Vn and some Vn plus m. So Vn plus m occurs after Vn. Okay. So I am going to use the triangle inequality, right. So I can pick some arbitrary point, let us say in between in the sequence, right. So we say Vn plus m by 2. I can pick some arbitrary point in the sequence which is Vn plus m by 2, and then I can say this is less than Vn plus m minus Vn plus m by 2 plus Vn plus m by 2 minus Vm, right. So I can write it like this, right. for the time being forget about the fact they are coming from a sequence. Just think of them as 3 points in space, right. So Vn is some point in that space, Vm n plus m is some other point in that space, and this guy is a third point in that space, right. So once I give you 3 points, I can use a triangle inequality, right. I just chosen the third point to be somewhere in between in that sequence, okay. So that's all. I mean, nothing to do with the fact that these 3 points are in a sequence. I can use a triangle inequality given any 3 points, okay. So I can do it this way, right. But there is nothing no sanctity about doing this. In fact, I can split this further. I can say Vn plus m by 2 and then n by 4, right. I can split that and do that. In fact, I can do this for every step along the way. So I am going to replace it with this. Right. So essentially n plus 1, n plus 1, n plus 2, n plus 2, n plus 3, so it keeps doing this. So I have repeatedly applied the triangle inequality to get this, right. Yeah.
T should take 2 points as input, right?
No, T takes from u to u.
Yeah, but
U to u takes u and then maps another point in u.
contraction with respect to y.
No, so 2 different points, right. So I take 2 arbitrary points u and v. This is for all points u and v in u, right. So any arbitrary point I take, I apply t on u and I apply t on v, right. So I'll get 2 resulting points, right. So I'll take the distance between them. They should be less than the original distance between u and v. Right. T is a mapping from u to u. It's not u cross u to u cross u, right. So it's a mapping from u to u. Okay. So now we have reduced it to the same t applied multiple times, right. So I can apply t, use this multiple times, right. So what I am going to get using this contraction operator here, is it fine?
Why did we apply t? Because it's decreasing.
What's that?
In the second step, we
Yeah.
applied the operator t because we found that it's decreasing. The distance between the two subsequent.
Why did I apply the operator t?
Yeah.
By definition, Vn plus k plus 1 is t operating on V1 n plus k times. Okay. Does it make sense? Now this quantity is independent of k, so I can take it out and sum over k. So what is the sum? I mean, it's very odd. I keep getting calls today. I don't know why. Like my third call during the class. So what can you say about this sequence? As n and m become large, it becomes smaller and smaller and smaller, right? As n and m becomes larger and larger, that sequence is going to become smaller and smaller. So this is a constant, so it doesn't matter. So as n and m become larger and larger, this is going to become smaller and smaller. So what can you say? The sequence Vn is Cauchy. Okay, people get that? Anything else we can say? We assume that's a Banach space, right? That's where I said Banach space fixed point theorems are easy. We assume it's a Banach space, therefore Vn is convergent. We already know that, right? So what needs to be shown now?